Imagine a triangle ABC and you pick any point P in its plane. Drop perpendiculars from P to the two sides meeting at C and call those distances X and Y. Here's the puzzle for a fixed distance from C. Where should P go to make the product XY as large as possible? Pause and think about it. Your first instinct is probably to set up coordinates for the whole triangle and optimize with calculus. That works, but it's messy. The breakthrough comes when you realize only the angle at C matters. Place C at the origin, with the angle bisector along the horizontal. The two sides make equal angles, alpha above and below. Now place P at distance D from C, at some angle theta from the bisector. This is our entire setup. Remember SOHCAHTOA. The perpendicular distance from a point to a line through the origin is just the distance times the sine of the angle between them. Think of it as the sideways component. The angle from P's direction to side CA is alpha minus theta. So x equals d sine of alpha minus theta, and the angle to side CB is alpha plus theta. So y equals d sine of alpha plus theta. Now multiply x and y. We get d squared times sine of alpha minus theta times sine of alpha plus theta. Notice the structure, sine of a difference times sine of a sum, with the same two arguments. That pattern should ring a bell from trig class. Here's the identity we need. Sine of a minus b times sine of a plus b equals sine squared a minus sine squared b. Why does this work? Expand each factor using the sum and difference formulas. The cross terms cancel perfectly, and we're left with that clean difference of squares. Now apply it to our product. xy equals d squared times the quantity sine squared alpha minus sine squared theta. Now stare at this expression. D squared sine squared alpha is a constant. It depends only on the fixed angle and the fixed distance from C. The only variable is theta. And since sine squared theta is always at least 0, we're subtracting something non-negative from a constant. The product is biggest when we subtract nothing at all. That means sine squared theta equals 0, so theta equals 0. And theta equals 0 means P lies exactly on the angle bisector of C. The maximum product is d squared sine squared of C over 2. This makes sense. The bisector splits the angle symmetrically, giving both distances equal weight. Balanced factors maximize the product. That's AMGM at work. So the answer is elegant. The product of perpendicular distances is maximized when P sits on the angle bisector. The key was one trig identity that turned optimization into asking when a sine is 0. This same bisector principle appears in optics. Light reflects, so the angle of incidence equals the angle of reflection. Symmetry wins again. If you enjoyed this, like and subscribe for more.